So today's lectures are going to cover steel, one of the 3 or 4 major structural materials that we deal with. And we'll talk a little bit about why we use steel, what its great advantages are, where we use it, what type of elements, and then also how steel is fabricated and how we have to detail around some of the issues that we have with it. As you can see, steel is super versatile. It has a number of ways that we can shape it, fabricate it, put it together with other steel elements. And as we've seen, it's a useful kind of adjunct to other materials that we typically use, like concrete. Steel is as versatile a material as we have to work with today. It's exceptionally strong for its weight. And therefore, we need relatively little of it to carry loads that, for instance, for concrete, we would need much larger volumes or much larger amounts of. It has this very, very careful balance between strength and compression and tension. It's one of the few materials in the world that is equally strong in both. And therefore, this makes it very good for elements that we put into bending, beams and girders in particular. Because that means that essentially when we're designing a beam, we can design it symmetrically if it's being loaded symmetrically, because compression and tension values in steel are relatively equal. Whether we turn a beam upside down or not doesn't really matter. There are very few other materials that we can say that about. If you think about reinforced concrete, for instance, we have to be very conscious of where we're putting the reinforcing steel in it. We have to think about the loading conditions and tune a beam based on that, where we put the steel, where we anticipate tension to be. If we're designing that same beam or girder out of steel, it doesn't really matter. It's going to be equally strong no matter which way the element is in bending. One of the other things that we tend to forget about steel is that we can fine-tune it chemically as well. Just like concrete, where we can change the recipe of concrete to make it stronger or more or less ductile, we can change the recipe of steel. We don't do this using admixtures. We do this using what we call alloys, right? Different mixes of iron, other materials like often nickel or cadmium, that can change the performance of the steel element that we end up with. The primary way we do this is adjusting the carbon content. More carbon makes for steel that is generally stronger, but also more difficult to work. And the sort of fine balance that we have typically is what we call architectural steel, or A36 steel. Finally, the steel industry has been very good about documenting what its products do. And for over 100 years, we've been able to get from steel fabricators a standardized set of products and also an awful lot of engineering data on those products. Because steel is made in factory conditions, it's very predictable. And structural performance is something that can be tested and published. And the American Institute of Steel Construction publishes a handbook that basically tells us exactly how every shape that is commercially available in the world is going to perform under given structural circumstances. So it's strong, it's versatile, it's adjustable, and it's also knowable, right? We know how steel is going to perform. Because A36 steel has this very precisely tuned carbon content, it's a really good balance of strength and stiffness. It's a very ductile material, so it can bend without breaking. This also means that it's relatively easy to work. We can hot roll steel by heating it up, not melting it, but just heating it up. We can put it through rollers and adjust its shape very easily. Its ductility also means that it's relatively easy to drill or to cut. This was not the case with cast iron, the predecessor to steel, which had to be molded into shapes and whose carbon content was so high that it was very brittle and couldn't be drilled or cut at all. We can do that very precisely with steel elements, and therefore we can fabricate them in ways that give us a lot of versatility on the job site, but also in very, very precision engineering, right? Precision production. Steel's ductility also means that if we're anticipating a lot of movement or a lot of deformation, this is one material that can handle it. Concrete is going to crack or break if we deform it very much. Steel is going to give. It has a very, very wide elastic range. And therefore, for a project like a bridge, it's going to be very handy because it's going to absorb that movement or that deformation without any permanent damage to the structure. We can manipulate steel in a lot of ways. We can design it to be fabricated with holes in it or with slices taken out of it that, because of its ductility, aren't going to affect the rest of the steel element. Obviously, when we put a hole in a structural element, we're removing some of the structural capacity. But steel is able to tolerate a fair amount of working. We can slice it, we can cut it, drill it, punch it, and the material around those holes or those alterations isn't going to be changed very much. This allows us to make a variety of connections that can take advantage of the sort of precise formation we can get to get things like hinges or rollers. Here on the left, you see a very precise roller connection that allows one element to move horizontally while still taking the vertical load of the other. On the right, you see a typical set of hinge connections where steel has been formed into elements that take and collect the load from these timber struts. They bring them down onto connections that allow the struts to rotate so that the roof of the structure can move around a little bit without twisting the foundation basically out of the ground, without transmitting the bending forces from one element to the other. Very difficult to do this in a lot of other materials because we don't have that precision engineering or that precision fabrication that can make a really, really tight pin connection. These can reliably transfer axial forces and they will distribute or get rid of the bending forces that those might bring into the base. So here, a kind of great example of steel's versatility is the Krauss Center, Renzo Piano building in Des Moines. Here you can see in construction, there are all kinds of manipulations that have been done to the steel structural elements. In some cases, to make them perform structurally with one another, you can see some of what we call torque boxes here, where elements are welded in between the flanges of this girder to make a kind of monolithic connection with the beam behind it. Here too you can see, here's the torque box. Here you can see tabs being welded onto this beam to allow for connections that are going to happen a little bit later. And then one thing that you see all over the place are these holes that are cut into these girders that will allow the mechanical system of the building to get woven through the structure. If you look closely, you'll see that these tend to be placed toward the center of the beam. Really big ones will be framed so that the forces in the beam will kind of flow around it. But small elements that are placed close to the center or close to the neutral axis of these shapes won't affect the structural performance of the overall beam very much. We saw this when we looked at beams as a structural type. Steel lends itself well to this kind of manipulation because it can be rolled in very thin sections. So these beams, these girders, all have sections that are less than ½ an inch thick, therefore easy to cut holes in it, easy to place those holes very carefully around the neutral axis where we know that they will do the least damage to the beam's carrying capacity, and therefore to integrate mechanical systems and structure into the same structural depth. We also have a great ability to mold steel into shapes that are not only efficient but also expressive. We can roll it, we can get steel sheets or plates, and we can cast it. And therefore we can make steel in just about any geometry we want, whether that's a linear geometry, a planar geometry, or one that's more three-dimensional. All of these fabrication methods have pluses and minuses. Some are more expensive than others, but depending on how much we want a given shape or a given form, whether that's a structural consideration or an architectural one, we have the ability in the shop to make almost any shape we want out of steel. We can recycle it relatively simply. We see this a lot in automobile manufacture, where old cars are often kind of farmed for their steel parts. We're beginning to see this come online in architectural structures too. Steel that in buildings that are being torn down is often recovered, recuperated, sent back to the mill to be molten down and refabricated into new shapes. And then finally, as we saw in the Krauss Center, we can take standard shapes, whether those are rolled or whether they're sheet or plates, and we can amend them, right? We can do things to those shapes to improve their structural performance. We can weld stiffeners to the web. We can add connectors that will allow us to very easily bolt pieces together on site. Or as we've seen, we can cut holes in it to allow for the passage of other systems. Incredible versatility that comes from the number of things we can do to it in the shop. It's worth saying that all of these manipulations that we do to steel, because they happen in a shop, in a factory, can be controlled very tightly. And so the tolerances that we get in steel are very, very, very precise. We can be assured that if we put a really tight tolerance on it, we can get things positioned on a steel element that are within a 1/16 of an inch, or sometimes within a 32nd of an inch when they show up on the job site. In concrete, of course, we don't get this. The formwork has to be placed. It can move around a little bit. We generally don't expect concrete to be placed with any tighter tolerance than maybe 1/2 inch on the job site. Steel is much more precise, and therefore we can get much more carefully tuned shapes out of it, both in the shop and on the construction site. Where do we use steel? Well, because of its versatility, there are very few places in a building structure that we don't use steel. We use it for collectors. We will use steel deck to form slabs. We'll use typically W shapes for beams and girders. And we will use steel also for load grounders, for columns in particular. Not so much for walls, although you will occasionally see steel shear panels between columns. But the rolling process, because it's a linear process, is very good for linear elements like columns. And there's a particular set of shapes that we'll often use called compact sections that come close to the radius of gyration value for hollow tubes, but without the expense of rolling those. We can, of course, roll steel into hollow tubes as well. A little bit more expensive, but if we're exposing those columns, then it may be something that's worth the budget to get an architectural shape. And finally, we'll see them in load stabilizers too. Cross bracing especially, but also steel elements that go between columns and girders to make particularly rigid moment connections that allow us to stabilize a steel frame without resorting to big panels of walls or cross bracing. When we're collecting loads, because steel is rolled, we're typically doing this in one direction. We can layer steel elements, though, to sort of mimic the two-way action that we get out of concrete slabs. We'll make floors very often out of corrugated decking, usually with concrete poured on top of this to create a durable surface, but also, as we've seen in our concrete lectures, to create essentially a series of linked T-beams that form the slab. And then we have a range of shapes that we can use to take the load of that slab, usually at right angles to the direction of the decking, out to a girder or beam. And if you look at these, you can see that we have wide flange shapes that have the kind of best possible shape for bending, webs that take flanges that take the compression and tensile elements of that bending, and then a flange between those that separates those and takes the shear that we get from the tendency of those flanges to sort of slide relative to one another. We can use other shapes. We might use a tube in an architecturally expressed situation. We might use a channel if we have some particular detailing needs. If we need to attach a lot of things to the web, it might be more convenient to put that web over to the side instead of the middle. And angles and double angles, very often we're using to connect elements of the load collecting system with one another. So angles are used very often to connect joists and girders, right? To bring a joist into the web of a wide flange girder and connect it carefully, making sure that we have enough bolts to take the load from one and put it into the other. When we use steel for load grounders or columns, we have a different family of shapes that we typically use. A deep, wide flange beam is going to be less efficient as a column because it will have one strong axis and one very weak axis. And if you remember from column theory, what we want is we want to eliminate any weak axis in a column shape. So the ideal shapes are over on the right. Hollow tubes, whether that's square or round, multi-axial symmetry, high moment of inertia because they're hollow shapes, and more importantly, a high radius of gyration. So no weak axis in any direction with a circular section and a couple of strong axial directions if we're using a square shape. When you go over to the left, you see that we get weak axes, which in columns means buckling. So the ideal steel shape for a beam is going to usually be a pour shape for a column. If we use what's called a compact section, though, we take a wide flange and we actually make it a less efficient beam shape, right? Bring the two flanges closer together so we get more of a square section. What we find is that if we put enough of the material into the flanges, we get shapes that begin to come close anyway to the moment of inertia, to the radius of gyration that we get with hollow elements. There are a couple of reasons we might do this. One is that hollow shapes are expensive to fabricate. They require being rolled around a mandrel and usually having a seam welded into them. So there are extra steps that we have to take in the fabrication process to get a hollow shape. The other problem with these shapes is that it's difficult to connect other elements to them. We'd like to get to both sides of a steel element when we're bolting it together so that we can hold a nut on one side and put the bolt through on the other. There's no good way to reach more than a couple of feet into a hollow section to do this. And so even though there's a trade-off in terms of pure structural performance, very often we'll use compact section wide flange beams for columns, in part because we can access both sides of the web, we can access both sides of the flange, and this makes it easier to connect other elements to those columns. Here you can see the problem of buckling. When we have a column that is sort of skinny and flat, we are worried not so much about the column taking the compressive load itself. We're worried about the column going into bending and basically buckling, getting out of the way of the load and leading the thing to collapse. The ideal shape, as we said, is on the left, column 1, which is a hollow round section. And you can see that both the flat bar in the middle and the attenuated wide flange on the right, those both have very distinct weak axes, and therefore we have to design the column for the weakest possible link. We're not taking full advantage of the material by doing that. We use steel for stabilizing, in particular for cross bracing. If we have bracing that goes in two directions, we find that one of those sets of braces is always going to be in tension. And what this means is that we can design relatively thin members. We're not worried about buckling in tension ever. And so in the New York Times building on the left If the wind is blowing left to right, then we have one raking set of cables that's going into tension, restraining the building, pulling it back. We have the other set of cross bracing going the opposite direction that's essentially going slack. Right? It's only one set of those, or only one direction of those cables are ever engaged at one time. When the wind reverses, then the other set of tension members picks up, right, and stabilizes the building in the opposite direction. This principle is great because it means that we use less material. In the situation on the left in the New York Times building, we're opening up those windows that might otherwise be blocked by thicker compressive members or by a shear wall. On the lower right at the Pompidou Center, you see cross bracing that is designed to take both compressive and tensile loading. And you get a sense for the scale there, right? They have to be designed basically not just as tension rods, but also as columns. And therefore that cross bracing is much, much thicker. Up here too, you see a really nice detail by Piano where cross bracing is coming in, and instead of, as at the New York Times building, sort of running past itself, here it all resolves into a single steel plate in the middle. All of these components, the turnbuckles, the pins, the plates, are made of steel. And this speaks a little bit to the versatility of the material. We've got basically cables here. We have cast turnbuckles there. Probably rolled cylinders here. And then the actual kind of plate looks to be cut out of a solid plate of steel and then drilled to provide access for the pins. One material doing a bunch of different things. Tension here. The pins clearly are in shear. The plate is going to always be in tension in one direction or another. And because we can form it in so many different ways, and because it's equally good in tension and compression, steel works in all of those situations, right? One material, several different functions. When you're designing steel structures for the labs, you can use these rules of thumb. You'll see that in general, we're a little bit thinner, a little bit more efficient than we are in concrete because steel is a stronger material. But the order of magnitude, we're kind of roughly the same. When we're designing decks in steel, we're looking at usually 1 to 24 for a floor deck, 1 to 40 for a roof deck, right? Because the roof load is so much less. And usually we're in the kind of 2.5 to 6 inch range for a floor, a little bit less for a roof. We'll talk in a second here about composite decking, ways to take advantage of the compressive strength of concrete, essentially where we had talked about reinforced concrete using steel in tension. In a composite decking, we're basically reinforcing the steel. We're using very, very thin steel decking, but we're detailing it in a way that it allows it to take advantage of concrete's compressive strength if we're pouring a deck on top. When we're talking about load collecting beams and girders and purlins, lightweight purlins, we can get down to 1/20th of the span for a roof. For floor beams and for girders, we're looking more at 1 to 15 or 1 to 16. And again, just a rule of thumb, similar to concrete, beams and girders, we like to have a sort of 2 to 1 to 3 to 1 ratio. When we're designing steel columns, we're more conscientious of buckling maybe than we are in concrete. The height of that column is going to be most important. We don't want to get, if we get over sort of 12 or 16 feet, we may find that we need to do the calculations to figure out whether we have a buckling issue. But generally, 8-inch columns, we can hold up to 3,000 square feet. 20-inch columns, we can go up to about 20,000 square feet. And again, we're going to check for buckling, and we're going to look at the steel columns typically to give us some idea of whether we need to increase the size based on the floor-to-floor height. We use steel in a number of other situations as well, beyond typical floor and girder and column construction. So because it's so easy to fabricate in so many different ways, we see steel used very often for trusses. We see it used for things like suspension structures. Again, taking advantage of the fact that we can get steel in tubes or in bar stock or in cables or in sheets or plates. And we can put it to work in a whole lot of different structural situations. We can fine-tune those elements too. We can take raw steel elements kind of right out of the rolling mill, and we can cut, slice, reconfigure them to take advantage of what we know about structural behavior. So here you can see, going from top to bottom, we can take what would ordinarily be a very simple but pretty dense rectangular beam. We can first roll it into a W shape so that we get some really distinctive flanges on the top and bottom, concentrating the steel's area where we know it's going to do the most work to resist tension and compression and bending. We can take that beam and we can castellate it. A castellated beam is where we make a sort of zigzag cut down the middle of the web. We shift the top piece over kind of half a bay, and you can see that those zigzags then become open hexagons. And if you think about it, those hexagonal voids are all occurring right on the neutral axis, right in the middle of the web where the material is doing the least work. So we're taking basically lazy material or dead material out of the center of the beam, and using the same amount of steel, we now have a beam that's a third again as deep, right? And we know from beam theory that that is going to be much more efficient, right? Separating those flanges, taking dead weight out of the middle of the beam, all of that is going to make for a much more efficient beam. And if you kind of zoom out even further, we could take that principle and apply it to make a truss. A truss is really nothing more than a very, very hyper-efficient beam. The top and bottom chord in this case are doing the same work as the flanges in a beam. So the top chord in a simply supported truss is going to be taking compression. The bottom chord is going to be taking tension. And the chords in between that form the triangular panels of a truss, these are basically doing the work of a web in a beam. They're providing, if you think about it this way, they're providing shear resistance to the two flanges, locking them in place relative to one another. The other way to think about it is that this is just a beam web that has almost all of its material taken away, right, by those triangular voids. You can think about it either in terms of a network of chords arranged in triangular patterns, or you can think about it as a bunch of very, very large triangular holes cut into an otherwise solid beam. Either way, what we're doing with all of these is we're taking our ability to manipulate steel, which is its kind of most important characteristic for us, to cut it, to weld it back together, to connect pieces of steel together. We're using all of those to make more and more efficient cross sections, to take dead weight out of the cross section, to concentrate our material at the top and bottom where we need it to do the most work, and to leave the middle of the beam with as much void space as we possibly can. When we go to castellated beams or we go to trusses, we're saving on material, we're gaining performance. The sacrifice is twofold. These are all going to be much deeper than if we just have a standard beam, so we're losing a bit of head space. And we're also spending more money on fabrication, right? We're doing more in the shop to create these more complex bending shapes. But this also allows us architecturally to make materials, to make steel into components, that are much more lightweight, much more finely tuned, that really do put the material exactly where we need it and nowhere else. So steel structures, particularly long span structures, are characterized by very precise structural form, right? We're following the lines of force as we've calculated them, as we've predicted them. There's no extra material. Everywhere we've got a piece of steel, in these examples anyway, we know that that steel is doing a lot of work to carry loads. That makes them a little bit more expressive. Our eyes can follow the load path from a roof, say, to walls and down into the ground. And we kind of like this as human beings. We like to see how structures work. You can see also that steel is capable of very, very lightweight structures. So any place we're trying to bring daylight through a glass roof or through a wall, steel means that we're taking up less space, we're taking up less volume, and we're allowing the passage of more light or more visibility or sometimes more ventilation, more air. We sometimes use steel as a hybrid with other materials to take advantage of these properties, but in sort of contained ways, right? Using like the smallest possible quantities of steel that we can, and letting other materials do what they're good at as well. We've seen this in reinforced concrete, where we're using steel to take the tensile the stresses in a bending element. We also use steel a lot in conjunction with timber, and we'll talk about this a little bit more when we talk about heavy timber construction. But one of the things that wood is not particularly good in is shear. If we're trying to connect two pieces of wood with a pin, if we put a big tensile or compressive load on those elements, the wood is going to shear, the pin's going to pull out or kind of slice through the wood before the timber element itself fails. And so when we're doing high strength timber, we very often find that we need to connect the timber to steel and then let steel do the work of connecting elements to one another. On the left, you can see timber cross bracing, and at the top and bottom of those cross braces, you see that they resolve themselves into these steel pin connections, very much like some of the ones that we were looking at earlier. This allows the cross bracing to rotate a little bit so that the building can move a little bit, and the timber can absorb that, can be a little bit ductile, but it's the steel that's actually allowing the members to pivot relative to one another. Wood, it would be very hard to make a pin connection just in wood, right? We worry a lot about that pin ripping through the grain of the wood. The upper right, you can see basically a three-dimensional timber truss holding up a roof, and all of those cords resolving on steel nodes that are built out of a combination of steel castings and steel plates. Again, resolving, in this case, the axial loads that are coming through that timber, using steel to create precise connections that allow for some rotation, allow for some ductility in the structure, connections that we couldn't make only in wood. And we also use steel very often to connect or to strengthen timber when we're putting pieces together. So because anytime we drive a nail or a spike or a pin through wood, we're not only reducing the capacity, but we're also to some extent damaging the fibers around it. We'll often use steel as a collar to hold on to one piece of wood, to seat it, and to connect it to a piece of wood below. And here you see some fairly typical connections where, in some cases, we're using steel to help put the pin into the wood and to make sure that we're not taking away too much strength from a timber element. In other cases, to make pin connections at the ends of timber elements that allow for some ductility, allow for some movement. Again, taking care not to put too much shear stress into the wood elements themselves, not to pull a pin through the grain, but to find ways to let steel do some of that work and to make the precise pin connections that we like in a ductile structure. There are disadvantages to steel. Because it's so precise, we tend to make it as thin as we can get away with, right? To use as little of the material as we can. And so steel is vulnerable to failures in buckling, but also on the right, as you can see, failure in shear. only because we can make it so thin. It's not necessarily a material flaw as it is our ability to be so precise, or to get steel elements designed so thin that we make them possibly vulnerable to some of these potential failures. Right, where the steel is thin enough or small enough to actually be really fragile. This is, of course, partly a problem that comes out of its ductility, but also because we tend to fabricate it in the thinnest possible sections. Steel is also vulnerable to fire. It doesn't burn itself, but it is not fireproof. The way that we make steel more ductile is we heat it up, and in a building fire, steel not only loses a lot of its strength, but it actually becomes a very, very viscous fluid, right? And obviously you don't want your structure to flow. So we correct this either by encasing it in concrete or building fire-resistant enclosures around it out of gypsum. Here you see a layer of 3 or 4 layers of, or layering of 3 or 4 sheets of gypsum drywall around a steel column. We can also use spray-on fireproofing that gives it a couple hours, 2 or 3 hours of protection, or we can encase it in lightweight vermiculite, something like that. We sometimes also see steel that has some kind of fire-resistant fluid, water often, actually ingrained in the steel structure itself. We tend not to do this anymore because, as we know, steel is also vulnerable to oxidation, right, to corrosion. Maybe the thing that we worry about most these days is that steel is an incredibly energy-intensive resource. We need to both extract the steel from the ground, right, to pull iron ore out of the ground. We then need to take, usually using coal, that steel and put it in an incredibly hot blast furnace, a very energy-intensive blast furnace. Once that molten steel comes out, we need energy, usually electricity, to turn that molten steel into slabs and then to roll it into plates or tubes or W shapes. If we're making sheets or plates out of it, we need additional energy to actually flatten it out. Right? So we're using coal for the blast furnace, and then we're then using typically a lot of electricity to drive the machines that actually shape the steel. And when we expose steel to outdoor air, like I said, we worry about corrosion. We all know that steel rusts. One of the problems with this is that oxidation not only kind of chews away at the steel section, so over time there's less and less material there, but as we talked about when we were talking about rebar, oxidation also makes the steel kind of blister, right, and puff up. And this can put an incredible force onto connections that we maybe had not anticipated. It's also unsightly. We don't like to see rusted steel. There are alloys, for instance, Corten, that rely on oxidation to protect steel beneath. These are sort of varying popularity, right? The general public does not like to see a rusting steel building, typically. And we guard against this in a couple of ways. We can either use alloys to guard against corrosion. So stainless steel uses additional nickel to create a very, very thin molecular layer of protection that prevents oxygen from reaching into the kind of inner steel core. Stainless steel is very expensive. More typically, in exposed steel, we will paint it, which keeps the moisture out if we put the paint on correctly and thoroughly. Paint, of course, scratches, though. We can use metal coatings, zinc or aluminum. We can anodize this onto steel to provide an actual metallic barrier. Again, one that is vulnerable, however, to scratching. And maybe the most popular one of these involves putting steel members into a molten bath of zinc. This we call galvanizing. We're limited in the size of the galvanizing operation we can get to, so you need a tub big enough to put your steel into. But this gives us an alloy layer on the surface of the steel that prevents it from rusting. Because we're dipping it into a liquid, we get all of the surfaces taken care of. And because it's not a painted surface, it's slightly less vulnerable to scratching. Galvanized steel has this very sort of trademark, almost glittering surface, right? You see the kind of elements of zinc plastered all over the exterior of the surface. Very good for high traffic areas, for railings, for things that are exposed and that are either going to be difficult maybe to paint or to maintain, or in buildings where we don't anticipate there being much of a maintenance budget, storage buildings in particular. There's some disadvantages to this. Ecologically, it's an extraordinarily toxic process, both to human beings working around a galvanizing tub, but also in terms of its byproducts and waste products. And it's also a very, very difficult material to weld because you're welding through a zinc coating on the outside. And that gives off both incredibly toxic fumes and also, of course, violates the zinc barrier that keeps water out. So if we're galvanizing elements, we tend to want to weld them first in the shop, then to galvanize them, and only to bolt them on site. So in the second half of the lecture, we'll talk a lot about steel connections, how we make them, how we tell people how we want steel to get connected, and ways of putting things together both in the shop and on the site that take advantage of steel's ductility and its versatility.